Okay, welcome back. Now that we've covered the topic of adiabatic expansion, we're going to do a couple examples with it. The example 1 says a diatomic gas N equals 20 moles is expanded adiabatically from an initial temperature of 25 Celsius and pressure P is 1 atmosphere. So that is its initial pressure, 1 atmosphere, to a final pressure of 0.2 atmospheres. Then its pressure rises isovolumically to some pressure P prime. In the third stage, the gas is brought back isothermally to its initial state. So what is V initial, V final, T initial? What is P prime, T prime? Find Q, W, delta E of each stage and the Q total, W total, delta E total of this whole process. So let's draw a picture of what this looks like. So it's always important to draw a PV diagram and to visualize what is happening. The initial pressure is 1 atmosphere. Right, 1 atmosphere. We know the initial temperature is 25 Celsius. We don't know the initial volume, V initial. So it's some, the atmosphere is 1 atmosphere, the volume is some volume V initial, right? So then you're going all the way down adiabatically, right, to some pressure, and then the pressure is 0.2 atmospheres, 0.2 atmospheres, right? Then we are going up isovolumically. So this volume here, we can calculate what that is. V, that one is called V final, right? V final. Then we're going up isovolumically to some pressure, right? But then it doesn't tell us what that pressure is, and it doesn't tell us what that temperature is. So we can call this one P prime, T prime, right? Then it says in the third stage, the gas is brought back isothermally back to its initial state. So isothermal, we go back isothermally. Remember in the theory section I explained to you that how an adiabatic expansion is more steeper than isothermal. So you can have adiabatic here, and then you can go up, and you can still go back isothermally because the isothermal is not as steep. So then you're going back to its initial state, right? So we want to know also how much heat is coming into the system, how much work the gas is doing, and the change in internal energy of each state. Okay, so let's start then. So the first thing we can do is find the initial temperature, right? So we can say here P initial, V initial is equal to nRT initial. The initial pressure was 1 atmosphere, and that's 1.013 times 10 to the 5th pascals. So we convert the atmosphere to pascal. The initial volume we don't know, right? V initial. The number of moles is 20, the gas constant 8.314, the initial temperature was 25 Celsius, so 273.15 plus 25, right? We put this all in and we calculate the initial volume. V initial is 0.4894 meter cubed. So that's going to be an initial volume here, 0.4894 meter cubed, right? Okay, so then we can find the final volume, right? What's the equation governing the adiabatic expansion? We have P initial, V initial to the gamma is going to be P final, V final to the gamma, right? I'm going to assume that this diatomic gas behaves regularly, so the gamma is going to be equal to 7/5, which is 1.40. Remember that there were exceptions to the rule. Some of the diatomic gases behaved a little bit differently, and then we needed quantum mechanics to explain the differences. So their gamma was slightly different, maybe 1.42 or 1.38 or so on. But let's assume a regular diatomic gas behaving regularly. So then we have gamma is equal to 7/5, which is 1.40. So then we can say here the initial pressure. This one I don't have to convert to pascals. I can keep it to atmospheres because it is actually just a ratio, okay, so a matter of ratio. So the initial pressure is 1 atmosphere. The initial volume is going to be 0.4894 to the power of 1.40. The final pressure is going to be 0.2 atmospheres. The final volume, we don't know, and then raised to the power of 1.40, okay? So then the atmosphere cancel, right? So then the final volume is going to be V final 1.40. Okay, so then the 1/0.2 and then 0.4894 to the power 1.40, right? So then you can calculate that. And then what you're going to do is you're going to raise both sides 1 over 0.2, 0.4894. What you do is just 1 over 0.2, which is what? 1 over 0.2 is 1/5, right? Which is just 5. So basically you're just going to have here 5 to the power 1 over 1.40 times 0.4894. Okay? So 5 to the power, then on your calculator you can do 1 divided by 1.4 and then times 0.4894. Then you're going to have 1.5. V final is going to be 1.545 meter cubed. Okay? Okay, so that's going to be our final volume, 1.545 meter cubed, right? How about the final temperature? This question meant actually to say what is the final temperature, right? The initial temperature we already knew was 25 Celsius, but what is the temperature right here? We can call the temperature here T final, right? So then we can just do the ideal gas law, right? Back to the ideal gas law, we can say P initial, V initial over T initial is equal to P final, V final over T final, Kelvin. Remember one important thing, when we do the temperature ratio, we have to do it in Kelvin, because a ratio of two temperatures in Celsius is different than the ratio of those same temperatures in Kelvin. The atmospheres, we can keep it in atmospheres because the ratio of two atmospheres is the same as the ratio of 2 pascals. And then the volume, we can either keep it in meter cubed, or if the volume was given in liters, we could also keep it in liters. But the temperature is the only one that it has to be in Kelvin. Okay, so now we know the final temperature. Okay, so now we can find out what the P prime and T prime is, right? Well, we know that the back step going backwards is isothermal, right? So the temperature here, T prime, must equal the same temperature as the initial temperature, right? Because this step is isothermal, so the temperature doesn't change. So this is the quickest clue what T prime is. T prime is also equal to T initial, okay? So T prime is equal to T initial, so that one we already know, okay? Well, if that's the case, then we can know what P prime is, right? Prime is equal to 0.317 atmospheres. It's gonna be the pressure right here. So you can tell the pressure here was 0.2 atmospheres, and then the pressure here is slightly larger, 0.317 atmospheres. Then we're going to go back isothermally from that point on. Now we know pretty much all the unknowns. Okay, we know the temperature at this corner, we know the pressure at this corner, we know the volume, we know the pressure, volume, and temperature here, and we know all the unknowns at every corner, right? So now we can do the heat of each step, and the heat in step 1 is equal to delta E of stage 1 plus the work done by the gas in stage 1, okay? But since stage 1 is adiabatic, we know that the heat into the gas in stage 1 is 0, right? Then you're going to have delta E 1 plus work, so this is going to be 0. Well, delta E of the gas in stage 1 is going to be what? Since the gas is diatomic, it's going to be 5/2 N R delta T. So all I have to do is just say 5/2. The number of moles is 28.314. The final temperature, which was the temperature here, 188.25 Kelvin. This temperature was actually the same as the initial temperature, so I wrote it wrong. That was the 273.15 plus 25, 298.15. 298.15. So I always like to draw the pressure, the temperature and the volume at each corner, so I know explicitly what is going on. The V prime is equal to 1.545, right? And then the temperature here is 188, and then the volume we know is 1.545, and then the pressure we already know is 0.2 atmosphere. So it's, before you do any of these calculations, it's good to draw each one and then to write down, and so you can know exactly what is happening at each corner, right? So then you can say here, delta E of gas 5/2 28.314. Okay, and then the final temperature is 188.25 minus the initial temperature which we started out with, which is 298.15. Okay, so then you do that. So then what's the work by the gas? Well, since Q is 0, the work by the gas will be, it's going to be negative delta E1, so it's just going to be positive 45.696 kilojoules. So that's how much the gas is doing work in this stage 1. Graphically, what that means, it's the area under the curve. For stage 1, like this, as the gas is going down, it would be the area under this curve like this. This bottom portion, right? If we shade that, that is the work done by the gas, 45.696. Now the other way to calculate the work by the gas, and we can do this just to make sure our answer is correct, the other way to do that is to take the integral, right, of PdV, right? So we can say here, let's erase this portion. Work by gas is equal to integral PdV, and then we can say here PV to the gamma is a constant, right? Right, so then it's just equal to, the constant is just equal to whatever the P initial was, whatever the V initial was over the, to the power gamma, right? So we can say the general equation for P is P initial, V initial to the gamma over the V to the gamma. So then we can say here this is P initial, V initial to the gamma over V to the gamma dV from V initial to V final, right? So then the P initial and the V initial are just constants, so we can pull them out of the integral, right? So then we're going to say here work by the gas, okay, is going to be P initial, V initial to the gamma dV to the power V, and then the gamma was 1.40, right, 1.40, and then the initial volume was the 0.4894, and then the final volume 1.454, and then we can put in these constants. Work by the gas, the P initial was 1 atmosphere, and then the V initial was 0.4894, and then the gamma was 1.40, right? And then the integral of the 1 over 1 V to the power 1.4 is going to be what? Well, you're going to have here P initial, V initial to the gamma, then you're just going to have V to the power negative 1.40 dV, right? And then you're going to have here what? P initial, V initial to the gamma, so then you're going to have the integral of this is V to the negative 1.40 plus 1 over negative 1.40 plus 1. Then you're going to have here V initial, P initial, V initial to the gamma. So then you're just going to have here negative 1.4. So then that's going to be negative 0.4. And then that's going to be negative 0.4. So 1 over V to the 0.4. Then you're going to do here V initial 0.4894 to the power 1.545. Okay? So then, since you have a negative here, that negative is going to switch the limits of the integral, right? So then you're going to have work by the gas. Then you're going to have P initial, which is 1.013 times 10 to the 5th. Then you're going to have the V initial 0.4894 to the power 1.40, right? And then you're going to have here, this negative is going to switch that integral, so then you have the 0.4 on the bottom, right? Then you can put this one in first, 1 over 0.4894 to the power 0.4 minus 1 over 1.545 to the power 0.4. Now hopefully if we do all of this, it will tell us that the answer is the same as what we got by the delta E, right? Which is the quicker way of calculating this answer. So let's do this here. So I get pretty much the same answer to within a rounding error. So just a little bit rounding, because when we're doing these volumes and the temperatures, we are probably slightly rounding, but pretty much it's the same. So we're going to get here 45.696 kilojoules. The answer actually gives me 45.686, but again, I'm just going to round it up, make it equal to the other answer that I got by the delta E, because it's just pretty much rounding error, right? So then you have here 45.696 and kilojoules, so then it proves that the two answers are the same, right? So if you had to do it the quicker way, you would just do the delta E, and then this would be the more elaborate way of doing it, and then you can show that the answers are the same, okay? Now let's find out what the Q and the W and the delta E is in the second stage, right? So with a different color, so we can see all the information that we obtained. Okay, so now what's going to be in the second stage? Q1, Q2, we can say, is delta E2 plus the work done by the gas in stage 2. In stage 2, the gas is going up isovolumically, so it does no work, right? So W2 is 0. So you just have basically delta E2 and Q2. So the easy way is just to calculate the delta E2, 5 halves times NR delta T. So you're just going to have 5 halves times 20 times 8.314 times the delta T. Well, then just take the temperature here, 298.15 minus 188.25. That will immediately give you both the delta E2 and the Q2, right? When we calculate that, it actually shows that the answer is the same as what we got before, because the change in temperature is the same. Here you were going from 298 down to 188, then you're going up from 188 back to 298. So the delta E is positive 45.696. And then the Q2 is also positive 45.696, right? So the numbers are the same, except that the gas is just doing no work. So we can put that answer here, okay, on the side. So I'm just going to erase this information now. On the side here, Q2 is equal to 45.696. That means heat is actually going into the gas in this second stage, whereas here no heat was coming in, right? So heat is going into the gas, and then the delta E2 is going to be 45.696. Okay, now let's do the last stage, okay? So then we have here, okay, Q3 is equal to delta E3 plus, and then the work done by the gas in the third stage. Well, in the last stage, it's isothermal and the temperature of the gas doesn't change. So delta E3 is just 0, right? So then the Q3 is just going to be the work done by the gas. And the work done by the gas, this is an isothermal process. So the work done by the gas is the area under the PV diagram. And as we've seen that before, what is that equal to? It's equal to integral PdV. But since in an isothermal process, PV is equal to a constant, right? So the constant is just equal to nRT. So we just have P is equal to nRT over V. So then it's just going to be nRT dV over V from V initial to V final. And then this is a natural log function, right? So Q3, which is equal to W3, is going to equal 20 moles, 8.314. The temperature is the temperature that it had during that isothermal process, which is your 298.15, right? 298.15. Ln V final is my V initial, right? 0.4894, because we're going backwards here. And then the V initial is my 1.545. So of course this is going to come out negative, right? 8 kilojoules. Okay, so then that's going to be the work and the Q3. That means the heat is coming out of the gas, right? So heat is coming out of the gas right here. Q3 is going to be negative 56.993 kilojoules. Or if you just want, you can just say positive 56, because we already said the meaning of the negative is that the heat is coming out of the gas. So you don't have to put here another negative. You can just say Q out of gas is positive 56.993. Or you could just say Q3 is negative 56.993, and the negative means it's coming out, right? And then the work in stage 3 is also going to be negative 56.993. So now if we sum all of these up, what should happen? Delta E total is going to be, well, here in the first stage you have negative 45.696. In the second stage, 45.696. So it should be 0, right? And it is 0 and it should be 0, right? Why? Because we're starting with a certain initial temperature and we're going back to that same initial temperature, right? So the total change in internal energy of the gas should be 0, and it is 0. So the third stage had no change in internal energy, and that was good because these two canceled each other out, right? Okay, how about the Q total? Q total is going to be equal to Q1 plus Q2 plus Q3. But Q1 was 0, so you just have Q2, which is 45.696 minus 56.993, right? Kilojoules. So overall, heat is coming out of the gas more than coming into the gas, right? And then we have here the work done by the gas is going to be equal to the 45.696. And then in the second stage, there was no work done by the gas. And then the third stage, it was negative 56.993. And then it should equal negative 11.307 kilojoules, right? So these two should equal to each other. Why? Because if the delta E total is 0, then the Q total and the total work done by the gas, this is total. These two should equal to each other because the delta E total was 0, right? In chapter 22, which is the next chapter, we're going to introduce a concept known as the efficiency. So if we consider this like a heat engine, then we're going to say, what is the efficiency of that heat engine? We can apply that concept now to this problem. So what would be the efficiency of that heat engine? The efficiency is how much the work the gas does, work done by gas, over the heat coming into the gas. Okay, in other words, how much heat do we have to put into the gas in order for the gas to do this amount of work? So then we can say the total work done by the gas is going to be negative 11, right? Well, if we want to run this as a heat engine, we would have to run it the backwards way. We would have to first go isothermally, we would have to go this way, isothermally down this way, reverse the direction, then go downwards isovolumically, and then go backwards adiabatically, right? This way, and this way. If we do that, everything just reverses direction. This becomes positive, this becomes positive, and every single positive that's here becomes negative, all right? But the zero stays 0, of course, right? So then the total work done by the gas will be positive, the positive 11.307, right? So it'll be 11.307 kilojoules. How much heat would we have to put into the gas for this heat engine to perform this work? Since everything would reverse itself, right? This one would be the Q3 would be positive 56. Remember in the third stage when we were going this way, the heat was coming out of the gas and it was 56.993. Now, since we're going backwards, the heat is coming into the gas here, into the gas. So this one becomes positive, and over here it reverses direction, and the heat is coming out of the gas, and then this one would be negative, right? And of course delta E2 will be negative. So in order to calculate the efficiency, we don't care about the heat that's going out of the gas. That's just the heat dumping into the atmosphere, right? All that matters is the heat going into the system in order for this engine to perform the work. So the heat into the system would be 56.993 kilojoules. Then these two would cancel, and then that would give us the efficiency of this heat engine. 19.8%. Okay. So next, I'll do an example that's related to this. We can go this way, isobarically. Then we can come down isovolumically. Then we can go back adiabatically. So we can reverse the direction, so we can model it more like a heat engine, and then we can also calculate its efficiency, okay? Thank you very much.